Section 1.3, the role of units in problem solving. Now we'll see how we can actually use those units. So first off, we're going to often need to convert our units. So you might have to convert from the English system to the SI metric system. And so in order to do that, we have a conversion between 1 foot is 0.3048 meters, a mile is 1.609 kilometers. There's horsepower to watts, and a liter to cubic meter, which this one's a really convenient one, right? Notice it's very precise, which is really great. These are things you don't have to have memorized. They'd be provided to you on the exam. You just have to know to look them up, that this is a resource that you have in order to convert said units. So how do we use these equal relationships in order to convert our units? Well, let's look at an example. The world's highest waterfall. The highest waterfall in the world is Angel Falls in Venezuela with a total drop of 979 meters. It sounds like a lot. Express this drop in feet. So we're going to use that conversion factor this is just the inverse of the one that was on the previous slide, that 1 foot is equal to 0.3048 meters. If you flip the numbers around, you'd get that 3.281 feet is equal to 1 meter. So since that's true, we can divide either side by the other side, and we'd find that it's equal to 1. Let's show this explicitly, actually. So first, starting with the original 1 feet, or 1 foot is equal to 0.3048 meters. And if I divide both sides by 0.3048 meters, then what we'll see is on the right, this will cancel out, right? The numbers will cancel, and then the units of meters, we can treat them like algebraic quantities, so they'll divide out too. So on the right, we'll have 1. And on the left, if you divide this out, you will get 3.281. So I encourage you to check that yourself. Don't just take my word for it. 3.281 feet per meter. So this is now a conversion factor because it's equal to 1, and you can multiply any number by 1 and it's not going to change it. That's a nifty factor. So if we want to go from meters to feet, well, then that means we want to be able to cancel the meters out. So that's why I wrote this with feet divided by meters. So that way I start with my length, that my length is 979 meters, and then I'll write as being multiplied by meters in the denominator with feet in the top. So that's my conversion factor. I'm just multiplying it by 1. So I'm not changing the number in any way, but it is going to change the units as long as I also include this number in here. So this means the meters are going to cancel because I'll have meters divided by meters. And so then I multiply the numbers that are left, 979 times 3.281, and that will give me 3,212, and the only units left are the feet, so it's 3,000 feet effectively. So there you can see how we can use the unit conversion factor. We're going to be doing this a lot, so if this feels uncomfortable, please ask questions in the discussion forum or send me an email, come by my office hours. I would love to talk more about this. Now with units, a lot of times there's prefixes in front of them, which is a little bit confusing. So you'll see this in front of the seconds or in front of the meters. And here are the primary ones that are used, right? Kilo, mega, giga, tera. That's the full written out word form of it. And then there's a symbol that's used to abbreviate it. And then this is the factor that's multiplied from the base. The base is 1, and that's just no prefix. And this is something you've seen in your everyday, but perhaps you didn't realize, right? Like you hear about the number of megabytes in your photos file size, or gigabytes or terabytes of storage space. That's just telling you how much more storage you have when you go from a mega to a giga, it's 1,000 times more storage. Or if you're into running, if you sign up for a 5K or a 10K, what's being implied there is that it's a 10 kilometer run. So the meter is somewhat implied, and the kilo is saying that it's 1,000 or 10 to the third individual meters. Our microscope is looking at things that are on the micro scale, so they're micrometer length. They're really, really small. We'll also use centimeter or millimeter quite a bit. Note centimeter is a factor of 100. There's 100 centimeters in 1 meter. Millimeter is where it's 1,000 millimeters in 1 meter. So here's a reasoning strategy for when you need to convert between units. So in all calculations, write out your units. Always include them, don't just assume them, because then you might make a mistake, as scientists before you have done. Then we'll treat the units as algebraic quantities. When identical units are divided, they're just eliminated algebraically, like we saw with the meters canceling, that left feet. You can use the conversion factors located on the page facing the inside cover of your textbook. Be guided by the fact that multiplying or dividing an equation by a factor of 1 does not alter the equation. So since you have something that's equal to something else, 100 centimeters is equal to 1 meter, then if you divide either side by the other that's equal to 1, you can multiply and divide anything by that, and you won't change the equation itself. The numbers may change, the units will change, the equation does not. So let's look at a more complex example here, the interstate speed limit. Express the speed limit of 65 miles per hour in terms of meters per second. And it gives us the conversion factors. Use 5,280 feet is equal to 1 mile, 3,600 seconds is equal to 1 hour, and 3.281 feet is equal to 1 meter. Right, so let's see here. We have 65 miles per hour. And this is incidentally what MPH is, right? It's miles per hour. And it's just suggesting that it's miles divided by hours, where hours are in the denominator there. All right, and we ultimately want to get to meters per second. So that's not involving miles or hours. And we can do any number of things here. The order doesn't really matter, as long as we make sure to change all our units. So I'm going to change the hours first, because that's in the bottom, and I don't want to forget that. And we have that 1 hour is equal to 3,600 seconds. So if I want to convert that denominator to seconds, then I want to cancel the hours. So I'm going to put the hours on the numerator to cancel it out, and seconds in the denominator. So now I'll have seconds in place of hours. The hours will cancel. And my conversion factor says that in 1 hour, there's 3,600 seconds. Cool, so that's a really great start. Now the hours cancel, and I have miles per second. So that's really good. You could get the number at this point, or you can keep multiplying, because you might as well, as long as you can keep everything straight, which is where writing it out really helps. So now I'm going to work on the miles. I want to get rid of the miles. It's not something I want to keep around. So now I look, okay, do I have any conversion factors with the miles? Oh, yes, I do, right? 1 mile is equal to 5,280 feet. Cool, so I can get in terms of feet instead of miles. That's not ultimately what I want, but it's an intermediate step. So let's see, 5,280 feet in 1 mile. And now when we check this, the miles are going to divide out, get a different color here, and we'll be just left with feet at this point, right? So right now we have feet divided by seconds, which is not yet meters per second. So, okay, we need to do a little more work. Mostly we need to get rid of that feet. So I'm going to put feet in the denominator to try and cancel it out. And I have a conversion factor of feet to meters. So cool. I want to get to meters in the numerator. This is really great. So I can say that 1 meter is this 3.281 feet. And now my feet will cancel out, and what I am truly left with is indeed meters per second. And I'll need to multiply all these numbers out. 65 divided by 3600 times 5280 divided by 3.281. Sorry, that 8 is a bit bad. And that will give me my final answer. So here it's shown, I'll get my drawings out of the way. Here they first solved for it in feet per second and got that's 95 feet per second. And then they multiplied by 1 once more with that ratio of meters to feet and found that the speed limit of 65 miles per hour is 29 meters per second. So I encourage you to check it, try it out yourself, see how it goes. Okay, one more thing. I mentioned units are your best friend. One, because when you write them out explicitly, like in the last one, you can make sure that you've done all your unit conversions properly. The other way units can help is with something known as dimensional analysis. And this allows you to check if your equations even make sense, or if maybe you made a mistake in copying it, which can have disastrous consequences. So for dimensional analysis, we say, okay, we'll say length is L in this brackets, mass is M in brackets, and time is T in brackets. Cool. We don't know if the length is actually meters or feet. We're just saying it has that dimensionality of being a length unit. So let's try it out. Is the following equation dimensionally correct? Well, we haven't fully covered these variables yet. That's really coming in chapter 2. So I'm going to fill in some of the information here. And if you're feeling a little overwhelmed going through it, that's okay. But X is going to be our position or displacement. So if you picture position, that's going to be going from A to B. That's a length. So I can write that the left side is length. Okay. The 1/2 doesn't have any dimensionality. It's just a number. So we don't have to worry about that. It still is a ratio, right? But it's not going to change the dimensions of it, the units of it. V is our velocity or speed. And we're going to see that speed is length divided by time, which we saw with the miles per hour, right? Miles was a length divided by hour is a time, or meters per second, length divided by time. So I'll write that out. So we have length divided by time, T. And then on the end, the T here is for time, and it is squared. So I can just fill in my time. I need to include that square, because that is an important detail. Now what we're going to check is how things cancel. So notice I have L divided by T times T squared. So I can divide out one of these T's, right? It'll cancel the square at least. But notice this is L times T, and that is not equal to L. So this would be not dimensionally correct. This is, turns out, not a real equation, right? So bummer. Or perhaps good, we said, hey, there's a mistake here. So let's try another one. Is the following dimensionally correct? I encourage you to try this yourself, so go ahead and pause your video, give it a shot. Okay, I'm hoping you did that. X, remember, is our length or position. Okay, and we want to find out, is it in fact equal dimensionally to the right? We aren't worrying about numbers here, just the units. And we remember V is our speed, so that would be meters per second, which is like length, divided by time, and then multiplied by time, which is just going to be time. And now look at what happens. The times perfectly cancel, and we're left with length is equal to length. So this one does in fact work out. We get that length is equal to length, and there is much rejoicing. So these were some simple examples. Let's try a more complicated one. So this is a think per share, where use the dimensions given for the variables in the table, not even knowing what the variables are, just knowing that they have this dimensionality. Determine which one of the following expressions is correct. So I want you to think about this. do work on your paper, take as much time as you need, but come up with one answer where you're like, I think it is this. I think it is A, and write that down. Could be even writing it on your phone. But I want you to choose an answer and be prepared to stick by it. No penalty if you're wrong, so might as well try. So go ahead and pause now. All right, so hopefully at this point you've taken the time to try and solve it. Now let's take a look. So we have this variable f that the dimension is 1 over time. L has a dimension of length, and G has a dimension of L divided by T squared. Kind of funny here. Okay, well, we can go through and take a look. The simplest one to me is to start with multiplication, because then I don't have to worry about fractions as much. So well, first off, the f is always going to be 1 over time. So we're always trying to get to 1 over time on the left side. On the right side, we have 2 pi. That doesn't have any dimensionality, no units with it. But it's being multiplied by L. So I could fill in L, and then times G, which is L divided by T squared. Keeping the brackets to show that these are not actual variables, they're just the dimensions. Now notice this is L squared divided by T squared. That is nothing like 1 over T. So it's not going to be this one. But based on how this one went wrong, we might have some other ideas, right? First off, if we go to E, this is multiplication again, but now it's with a square root. So we'd have L squared divided by T squared, but then it'd be the square root of that. Keeping the brackets. And when we take the square root of that, then we are going to just be left with L over T with brackets, which incidentally is much closer because now we at least don't have any squares. It still isn't matching what we ultimately want to. So this is also not true. But this tells me that the square root is actually going to be a helpful thing. So it's probably not going to be A. So this leaves C and D as more likely options. So we can take a look here. We know we want to end up with 1 over time. If we want to end up with 1 over time, I notice G already has time in the denominator. So I want to keep G in the numerator, I think. And if I divide by L, I think I'll be able to cancel that length. Let's give it a shot. So again, the 2 pi, we don't have to worry about the units there. So then I have my units of L divided by T squared times squared. And then this is all divided by L. And it gets a little bit tricky when you have fractions and division there. But remember, you can write this as the division of the bottom one as being multiplied by the inverse. So I'll come up here for that. So we have the square root of L, I'm going to drop the brackets for now, over T squared times, instead of being times L, it's going to be times 1 divided by L. And so that allows us to then cancel out these L's, and we're left with the square root of 1 over T squared, which guess what? That's just going to be 1 over T. So this one does check out, and you can try the others and they will not work out. You will not get the matching of 1 over time on either side. Incidentally, this is the equation of a pendulum, which we will get to see later this semester. So stay tuned for that. This introduces units and problem solving as well as how to do unit conversions. We're going to be using units a whole lot, so I hope that you stick with it and make sure you understand this, and I'm happy to help if and as you have any questions.